Okay, this is 4 questions from chapter 3, 3.1 of your grade 8 math links. This chapter is about squares and square roots. The first question we have here gives you 4 numbers and asks you to simplify them. So 4 squared. Since 4 squared means taking 4 and multiplying it by itself, the answer I'm looking for this is, what is 4 squared? It is 16. 6 squared means taking 6 and multiplying it by itself. So what is 6 squared? It is 36. Now this says the square root. You don't have to write this, but the square root of 100, which means what number when multiplied by itself is 100, or what number when squared is 100. Both ways are ways to interpret the square root, which means 10 when multiplied 10 by itself is 100, so therefore the square root of 100 is 10. The same thing with this one. What is the square root of 400? Of 400, meaning what number when multiplied by itself is 400? The answer is 20. Because 20 times 20 is 400. Question number 2 says, what are all the factors of 100? How can you tell if it's a perfect square? So if I was to write out the factors of 100, I would say, well, the first way I can get 100 is by multiplying 1 by 100. That means that 1 is divisible into 100, and 100 is divisible into 100. I can also get 100 by doing 2 times 50. So 2 is divisible into 100, and so is 50, which means 2 and 50 are factors of 100. I can also do 4 and 25. I can do 5 and 20. And I can do 10 and 10. So when I rewrite these factors, I would write them, and I just kind of use a horseshoe. So when I do it, I kind of think of it this way here. I just kind of go around like this. The factors of 100 are 1, 2, 4, 5, 10. I don't write 10 again because it's already used. That would be redundant. 20, 25, 50, and 100. So those are the factors, all of the factors of 100, which means those are all of the whole numbers that will divide evenly into 100 without giving you a decimal. The second part to that question says, how can you tell that it's a perfect square? Well, there are 2 ways to tell. The first way to tell is right here. So if I was to look at that factor, 10 and 10, because there is a number that multiplies by itself to get you 100, that is the definition of what a perfect square is. A perfect square is a number that's derived or created when you multiply a number by itself. So in this case, 10 times 10 gives you 100, which makes 100 a perfect square. The other way you could tell is by simply counting the number of factors. In this case, there are 9, which is an odd number. And the reason why it's odd is because when I do this one here, I didn't write 10 twice. I only had to write it once because I was saying what are the numbers that divide equally, which means 10 is itself doesn't have to be written twice. And every time you have that, you will always end up with an odd number of factors, because if it's a perfect square, one of them will be repeated, which means that is the odd number out. So you'll have an odd number of factors for perfect squares and an even number for non-perfect squares. Question 3 gives you this square, and it says the area of the square is 225. What is the perimeter? So we know that the area of a square, we learned, is side squared. That was the formula we used to figure out the area of a square. Now you might have used side times side. So if I asked you a different one, is its side multiplied by itself, or side times side was how we got the area of a square, maybe in grade 7 before we learned exponents of 2. So if I had asked you what number was multiplied by itself to give you 225, what number times itself? Well, what number times itself? Side times side. What number times itself is the same thing as side squared. What number did I square to get 225? Now, algebraically, and this is something that we did not talk about before, but I'm going to show it for you anyway. You can do it 2 ways. You can do it by inspection, or you can do it by opposite operation. So if I did it by inspection, I said, what number did you multiply by itself to get 225? You would say, I would have to multiply 15 by 15 to get the area of 225, right? But that's not done. That would be identifying what the side length is. If it's a square, all of these sides are 15. Would you agree? And therefore, the perimeter, which is the distance around the outside, would be 4 multiplied by 15. Or if you wanted to, you could do 15 plus 15 plus 15 plus 15, or 4 times 15, which means your perimeter would be 60. Okay? If the area of that square was 225, that means the side length must have been 15, because 15 times 15 would have given you your area. And if the side length was 15, multiply that by 4 to get the perimeter, and you would have the perimeter equal 60. Now, alternatively, instead of solving by inspection, you could have solved this algebraic equation with opposite operation. And this is complicated. If you get it, great, because we're going to do it later on as well. If you don't get it right away, don't panic. We will study it more in depth later. And remember, on a algebra scale, if I multiplied this side by 2 and I multiplied this side by 2, it keeps it equal. If I had a scale and I subtracted 20 from this side and I subtracted 20 from this side, it would keep it equal. But on this side, if I was to square root this side and I was to square root this side, according to the laws of algebra, it should still maintain equality, as long as whatever I do to one side, I do to the other. So if I was to square root this side and I was to square root this side, the square root of 225 means what number times itself is 225? The answer is 15. And the square root of s squared, what number did I multiply by itself to get s squared? The answer would be s. S times s was s squared. So by square rooting both sides, I've isolated the variable, and I've defined my side length as being 15, which I could plug in, and then utilize the formula 4 times the side length is its perimeter. And finally, your last question says, how many prime factors does 576 have? And is it a perfect square? So prime factorization. So what we want to do is we want to find ways we can multiply to get 576. If it's a prime number, we're going to circle it and call it a prime factor. If it's not a prime number, we're going to continue to branch that off until the entire number has been created by multiplication of prime factors. So because this is an even number, 576, I know that you can divide 2 into that number. So I'm going to take 2 out, and then I'm going to ask myself 2 times what is 576? Well, using a calculator, I can take 576 and divide it by 2 to realize that it's 2 times 288. Okay? So I have a prime factor of 2, which I've circled, and I have a composite number of 288, which can be further branched into product of prime factors. 288, because it's even, can also be multiplied or take a 2 out. And 2 times 144 is a way to get 288. But I'm not done yet because 144 is not a prime number. Now, there's multiple ways to do it. And at this stage, some people are going to go 2 times 72. Other people are going to say, hang on, I know that 144 from somewhere. 144 is created by multiplying what 2 numbers together? 12 and 12. So some people might do this, go 12 and 12, right? So I know that's how I can get 144. And if you did 2 and 72, that's fine. It doesn't matter because at the end, you're going to have the same answer in the end anyway. So neither one of those, 12 or 12, is a prime number. Remember, a prime number is one that only has 1 in itself as factors, or is divisible. So both of these can be created into a 2 and 6 and a 2 and 6. 2 is prime, 6 is not. And finally, the 6's can be brought down into being the product of 2 and 3, both of which are prime, and 2 and 3, both of which are prime. So when I analyze my tree, and I put down 576, 576 can be created by multiplying 2 by 2 by 2 by 2 by 3 by 2 by 2 by 3. So 2 times 2 times 2 times 2 times 3 times 2 times 2 times 3 will give me 576. And if you don't believe me, let's take a calculator and just double check. Bring it over here and go 2 times 2 times 2 times 2 times 3 times 2 times 2 times 3 equals, I made a mistake. I forgot a number. Is another 2 there? Hold on. Let's double check. 1, 2, 3, 4, 5, 6 2s. 1, 2, 3, 4, 5, 6 2s. 1, 2, 3s. Uh-oh, did I make a mistake somewhere? Oh, did I only press 2 once? Oh, maybe that's what it is. Let's try that again with the calculator. Let's try it again. All right, here we go. One more time, this time being a little bit more conscientious. Clear. Okay. 2 times 2 times 2 times 2. That's 4 2s. Times 3 times another 2 times another 2 times the final 3. There we go. Equals 576. So those are the numbers. So the answer to the first question is 1, 2, 3, 4, 5, 6, 7, 8. It has 8 prime factors. That's the first part of the question. But the second part says, is it a perfect square? Now, the associative property of mathematics says, if I was to multiply these numbers in any combination of order, I will still always get 576 because the order in which you multiply numbers does not affect the product of a number. So the question is, can I rearrange these 8 prime factors to make 2 identical groups? And the answer is yes. I can take 1, 2, 3 2s and one of these 3s and multiply it by the other 3 2s and 1 3. So instead of multiplying it 2 times 2 times 2 times 2 times 3 times 2 times 2 times 3, I can multiply it by 2 times 2 times 2 times 3 times 2 times 2 times 2 times 3. And the reason why we rearrange them, it's simple. Because now we see that these and these as a number are going to be identical, aren't they? So 2 times 2 times 2 times 3 is 8 times 3, which is 24. So another way I could rewrite this would be 24 times 24, which means, is it a perfect square? Yes, it is. How do I know? Because there is a number that I multiply by itself to get 576, and that's 24. I've used a calculator. 24 multiplied by 24 is 576. Or another way to say that is the square root of 576 is 24. Right? So 1, 2, 3, 4, 5, 6, 7, 8. Oh, because you said odd number, right? So his question is, you said in this question right here that because it was an odd number of factors, it was a perfect square. But here you said that's an even number. The difference between that question and this question is these are prime factors, and the other one was just regular factors, not prime factors. So there is a difference, and that's a good point, Hank. In all the years I've been teaching, I haven't thought of that, so that's a good point.